All right, I apologize for people watching the video after the fact. We're designing, let me recap real fast, a 4-bit 2-to-1 multiplexer in Verilog. We're doing a 2-to-1 mux first, and then we're going to expand it out to 4 bits. We got two data inputs, A and B. We got a control input C, and the output Y is equal to A and C prime, or B and C. So there we go. And now we've got our logic diagram for our 2-to-1 mux. So the next thing we need to do is make a 4-bit 2-to-1 mux. So what that means is we're going to create 4 instances of our 2-to-1 mux. The first one, we'll take A3 and B3 and give us Y3. The second one, we'll take A2 and B2 and give us Y2. The third one will get us A1 and B1 and give us Y1. And the last one will get us A0, or take in A0, B0, and give us Y0. And all of these guys will use the exact same control input C to make the selections. All right, if we were to draw that out using our bus notation, A, B, 4 bits to Y, and then 1 bit to C. So this is what we're going to build. We're going to do it in 2 steps. We're going to create our 2-to-1 module and test it, and then use that to create our 4-bit 2-to-1 module. So before we jump into Verilog, are there any questions about the design that we're going to attempt to build? Well, not attempt, we're going to do it. Okay, in that case, let me exit out of Notepad, close that because I don't need you anymore. I'm going to pull this up. I'm in Visual Studio Code. You can see all the stuff that we've been working on for the last couple of days. And I'm going to create a module now. I'm going to call it mux2to1.v. So it's module mux 2-to-1. It has parameters A, B, C, and Y. And our in-module declaration. And now we're going to make a distinction between data inputs, control inputs, outputs, and our logic circuit. So our data inputs are A and B, so we have input A, not inputs A, input A, input B, our control input, input C, and our output Y. And then finally, our logic circuit, we'll use, even though we drew out the logic diagram, since the symbol, yeah, except we're not going to copy and paste code, we're going to reuse extensible modules. So now what we're going to do is, instead of doing wires and stuff like that, since it's a simple circuit, assign Y equals, we'll do A and not C, or B and C. Just like that, as one single logic expression. And there we go. That's our entire multiplexer module. We've got data inputs A and B, control input is C. Make what a full-size window? It is a full-size window. What parts can't you see? It looks normal on my screen. Like with the name of the file. Like you're talking about like over here? I mean, I can't make that bigger. Yeah, that's what it's supposed to look like. I'm not sure. Oh, that's weird. Why is it doing that? Huh. Let's address that. Let's see what's going on here. I don't know, it's full screen on my... Alright, let's... Alright, kill that. Give me just a second, guys. We'll get it figured out. So it's full screen on my monitor. It even looks full screen there. You know what? That's totally possible, actually. Let's see. Kill that. Let me throw it up on a different... Let's try a different monitor. No, still not that. Let's try a couple other things. Actually, you know what, we're gonna do this. Screen. There we go. I'm just sharing the monitor itself, not the... No, let's go with that. For today, at least, and I'll figure out what the deal was. All right, so moving on. So we've finished our 2-to-1 multiplexer, and actually, you know what? Hold on, I'm gonna change this because it's on. I want to put it on a different monitor so I don't have to like stare at myself talking. Give me a second. Go over there, and then let's share that one. There we go. All right, so it's not like in my field of view. Okay. I haven't posted it yet, Devin. I'll post it over the weekend or on Monday. All right, any questions about the 2-to-1 mux now that we've got some of these technical issues out of the way? Someone's typing. 2 people are typing. Yes, I am recording. I think. Yes. So we talked about that when we talked about multiplexers in class a couple weeks ago. The question was, what is the difference between a control input and what they call a regular input? Here we call it a data input. So basically the difference is they're all inputs, and so under the hood there's really no difference between control inputs and data inputs. But we distinguish between the two because one has data, right, information that we want to manipulate, and then the control inputs sort of control manipulating that data. You can sort of think of data inputs and outputs as the inputs and outputs to the system, and control inputs let us manipulate what actually happens on the inside. But fundamentally, there's no difference between the two. All right, so let's go ahead and make a test bench for this. For every module you create, you should always create a corresponding test bench. So we'll say mux2to1 underscore tb dot v, and we'll lay it down. So time scale 1 nanosecond / 1 nanosecond. We're going to include our mux2to1.v file, and we're going to set up our module mux2to1 underscore tb not bt, semicolon, since there are no input or output parameters, there are no ports. And we'll set this up kind of the same way. Data inputs, control inputs, outputs, the unit under test, and the logic simulation. Just kind of organize our stuff here. Remember, in the test bench, we use regs for inputs. So we have reg A and B, we have reg C, and we use wires for output, so we have wire Y. Our unit under test is the module we're creating, so mux2to1 ut A, B, C, Y, semicolon. Now we're ready to set up our logic simulation. Initial, begin, and end. Let's go ahead and add our boilerplate. Dump file mux2to1.vcd, our dump vars 0 mux2to1 underscore tb, and our finish statement when we're done. Now let's go ahead and lay down the simulation itself, and well, let's take a look. Let's see, we're going to do actually we're going to create a for loop. So we're going to go all the way through all of the inputs. So I'm going to say for integer I less than 8, I equals I plus 1, begin and end. Remember, begin and end in Verilog are equivalent to curly braces in another programming language. And we're going to do this. We're going to say A, B, and C is equal to I. Yeah, we'll go ahead and do that too. Equals I. And we're going to delay for 10. And we'll even do one better, right? It's going to be tricky to look at the waveform and know what everything is working, right? Because you're going to say, all right, well, A was 0 and B was 0, so C is equal to 0. That doesn't really tell us anything. So what we want to do now is, well, see if it works or not. So I'm going to create an if statement, actually. I'm going to say if Y is not equal to, and let's go ahead and use the exact same logic statement as before. Now, in practice, you might not want to copy and paste your logic statement directly from your module in your test bench, because obviously if your module in your test bench is wrong, then well, then what you type is going to be wrong. but I'm pretty confident that my solution here is correct. So I'm going to type wrap everything in those guys. And let's say if. Dude, it's 2020, man. Nobody uses the increment operator anymore. It's all about expressive code syntax. And I equals I plus 1 is a more semantically rich expression. Haven't you gotten the memo about semantically rich code? You're right, semantically rich code instead of comments. And everyone knows what you're talking about. Some languages don't, some new languages, like anyone who does like iOS development in Swift, Swift doesn't even have the increment operator. They make you do both. I just don't have semantically rich code or comments. I just have soup. You just have garbage code. All right, so check this out. We got if, begin, and end. So if y was not equal to that, then we're going to output a message that says, yeah, garbage fire. Test case failed for minterm D, and we'll say for I. And then we can come down here, we can say else. Yeah, I'm not going to do that. Else begin and end display test case. You know, let's do this passed in all caps. I'll come up here and say failed. This, by the way, is approximately what I would do when I grade, my test benches for grading your Verilog projects. It's essentially this. It'll just, but it keeps track. It like scores you based on what worked and what didn't. Okay. So that was a lot. Let's kind of unpack what we just did here. The first thing we did was we wrapped everything into a for loop because we're modern programmers and we have for loops. And so instead of copy and pasting a bunch of stuff over and over again, we're just going to use loops to do it. Here is where we actually do the simulation bit. We say, you know, A, B, C is equal to I. So that's going to run through all of the possible minterms. And then here we're actually going to do a check to see if things passed or failed, right? If Y is not equal to what we know to be the correct syntax for a multiplexer, then we'll say that it failed. And if it else, then it must have passed. And we'll say test case passed for minterm. And then we'll take a look and see what we got. So any questions about this test bench syntax? We've done some sophisticated stuff. And by the way, I'm assuming that you all have taken or are currently taking your intro to programming classes, and at this point hopefully already know what things like for loops and if-else statements are. So modulo D is a placeholder, so it says, hey, put a decimal number there, and then when we comment out, we do, you know, Y, or do what we're going to do there. So it's just a placeholder for, it's called string interpolation. So we say I want to put a thing there, and then the value is going to be there. It is a much better way. You'll see, you know, programmers who aren't as good do stuff like this, right? You know, stuff like that where you add the midterms together. You know, and put a period or whatever. So don't do that. Instead, use string interpolation and live your life a lot better. So that was a roundabout way of saying it's going to put the value of I right there in the string. It might have been, yeah. So if you screw it up, it can lead to weird things. So let's go ahead and see what we messed up. I Verilog, option O, mux221.vvp, mux221_tb.v. Let's run it. Hey, look at that. We screwed some stuff up. We got syntax errors. Let's see. Syntax error, incomprehensible loop. Oh, you know what happened? I didn't assign an initial value for I. So I said I have no idea what to do here. Let's run it again. Hey, look at that. Now there are no errors. Now let's run the simulation. VVP mux 221.vvp. So here's where the magic will happen. And look at that. We got test case, all passes all the way down. So that's groovy. That's awesome. Just for fun, what if we went and changed, and I don't know, let's change this to and instead of or. And we run it again. Oop. Don't forget, if you make a change, you have to do Verilog from the top. You got to compile again, and then run your simulation. And then there we go. We got some pass or some failing cases. So it failed for 3 and 4 and 6 and 7, but passed for the other cases. When I write the test benches to grade your stuff, basically what I do is just say, integer score equals 0, and then in the case where it passes, I say, score plus equals score plus 1, and then down here at the bottom I'll say something like final score of 8 test cases score cores. This one would have gotten a 4 out of 8. Oop, yeah. Probably should have done that anyway. Alright. So we just did a bunch of crazy test bench stuff. But like I said, when I give you your test bench for your project, this is basically what is going to happen. Although I'll come up with some clever way to hide that. So you don't just copy and paste it directly. Okay. So, any questions about the multiplexer or the test bench? Okay, so now we need to do the 4-bit multiplexer. So I'm going to create a mux, call it mux 4bit.v. Those guys over there. And then now what we need to do is, first we need to include, since we're going to use our 2-to-1 multiplexer as in our 4-bit mux, we need to make sure to include it. Include mux 221.v. Now we create our module, mux 4-bit. And it's going to have the same stuff, A, B, C, and Y. End module. So, yeah, whoever wrote Icarus Verilog included some sassy terminal commands. So the important stuff is what is above the I give up, the actual syntax stuff. It does a bunch of other weird stuff. It'll first, if you do some kind of other strange errors, it'll insult you and tell you your code is garbage. It's pretty fun. All right, let's see. Control inputs, outputs, and our logic circuit. So now things are going to be a little bit different. We're going to say input. Now we're going to make 4-bit buses. So what we're going to do now is I'm going to use square brackets, and say 3 to 0. This will create, and that's going to be for my A. So that's going to make a 4-bit bus, right, with an A3, an A2, an A1, and an A0. And the order matters, right? We want to do the higher number on the left-hand side. So if I were to put this in comments, it would be A3, A2, A1, and A0, just like that. But if I were to do this, input 0 to 3 for my B, then it would flip things over and I would have B0, B1, B2, B3. So by convention in this class, and there's no particular right or wrong answer as long as you agree with whoever you're working with. But in this class, we're going to use what they call big Endian notation, where the leftmost bit gets the higher number. So this will be B3, B2, B1, B0. And the next up is the control input. Since it's still a 2-to-1 mux, it's a 1-bit control input. And then we'll have an output. Now our output is also 4 bits, so output 3 to 0, Y. And we're going to look at 3 different ways to implement this in progressing order of simplicity. The first one is the most basic way. We're going to create, if you've ever done object-oriented programming, this is going to look pretty familiar to you, but we're going to create 4 unique instances of this 2-to-1 mux module. So what I'm going to do is I'm going to say mux 2-to-1. I'm going to give it a name. By convention, we use like capital U and then 0. And then this first one is going to get, ooh, actually, you know what I'm going to do? I'm going to start with U3. And it's going to get A3, B3, C, and Y3, and then a semicolon. So what's happening here is so this mux, even though this is a 1-bit 2-to-1 mux, this one is going to get the 3rd bit, or the 4th bit, excuse me, of each one. And this notation is how we index it. Similar to how you would index an array in another programming language. And now we can just sort of copy and paste everything. So these are all 2-to-1 muxes, but this one is going to be U2, U1, and then U0. And I'll take U2, U1, and A0, B2, B1, B0. C always stays the same, and then Y2, Y1, and Y0. And that's all we need to do. So we've created 4 instances of a 2-to-1 mux, and this lets us do the thing. So now let's go ahead and create a test bench for it. So I'm going to call this mux 4bit underscore tb.v, and I'll do it over here on the right hand side. Same boilerplate, time scale, 1 nanosecond, 1 nanosecond. We're going to include mux 4bit.v. And then our module, mux 4bit, nothing in module. And let's set up the same stuff. Data, inputs, control, inputs, outputs, unit under test. Well, we're not setting, okay, so Liam asks, is A3 a name, so like this, or are we actually setting something as 3? Neither. We're saying we want to attach, so remember we created an input that's got 4 bits. There's an A3, an A2, and A1. And this notation, again, just like in your other programming classes, when you're working with arrays and you index an array, this works in the exact same way. We're saying that over here in mux 2-to-1, the first parameter is our A, and I want to assign that to A3, the 3rd bit of A, the 4th bit of A, from my data inputs, and all the way down. So then the next one says, I want to attach, since we're creating an entirely new 2-to-1 mux here, we're going to say for this one, we're going to attach its A to A2 up on top. You're totally right. This should be TB. All right, so same deal. Regs for inputs, but remember everything now is 4 bits. So reg A, 4 bits. Reg 3 to 0. B. Control input reg C. And output wire 3 to 0. Y. Our unit under test, mux 4-bit UT A, comma B, comma C, comma Y. And then our logic simulation, initial begin, and end. Now, there's a couple of different ways to go about it. We don't have a lot of time. So the most easiest way would be to just set some values. Like let's set A equal to, you know, a 4-bit binary number 0, 1, 0, 1. And set B equal to 4B 1, 0, 1, 0. And set C equal to 0. And then delay for 20. And set C equal to 1. And delay for 20 more. And call it finished. And that's actually what we're going to do here because, although actually I don't want to use binary. Remember, I can use D for decimal, so I'm going to make that 6. I'm going to make that 12. So it's still 4 bits, but it's representing it in decimal. It's 12 and 6. And let's add our dump file. Mux 4-bit dot VCD. Our dump vars 0 mux 4-bit underscore TB. And we're ready to go. So let's take a look at that. Clear. So let's compile. Verilog option O. Mux 4-bit dot VVP from mux 4-bit underscore TB dot V. All right, made some errors. Syntax error at line 17. Oh, so here's an example of it says syntax error at 17. There's nothing wrong here, but at 14, the next code line up, I forgot a semicolon. So let's try it again. There we go. VVP mux 4-bit dot VVP. We created the file. Now let's go GTK wave mux 4-bit. It's Friday. It's the last lecture of the day. I'm having a hard time like paying attention to what I'm doing. Okay, now let's take a look. All right, so here we set some initial values and everything seems to be in order, right? So we start at the beginning. A is equal to C, B is equal to 6, C is equal to 0, so A should be equal to so C is 0, so Y should be equal to C, right? And here, C is equal to 1, so Y should be equal to 6. Something has gone wrong. Let's take a look. A, B, C. Reg C, wire. Input A, input B, input C, A, B, C, Y, A, B, C, Y, A, B, C, Y, 3, 2, 1, 0, 3, 2, 1, 0, 3, 2, 1, 0. Let's leave some of this other stuff. So, what happened? I'll try something first. I'm going to put a delay after I set these values. I don't think this will make a difference, but I want to take a look. This didn't happen in the morning lecture. Yeah. So notice this red wire means that since we waited for 20 nanoseconds to give C a value, C remained undefined until 20 nanoseconds, and then it clicked to 0, and then to 1. But why isn't that working? Let's see. Does anybody out there see why? That's good. All right, instead, we're going to demonstrate how to debug a Verilog circuit. This is obviously a thing that can happen during your stuff. So one of the things we can do is we can sort of drill down and we can look at our individual pieces, right? So we created U3 to U0, and we can actually go down and take a look at them. So let's look at U0 and see what happened. Actually, let's look at U3 and see what happened as well. So in either case, the signal did not click over when it's supposed to. So our 2-to-1 mux isn't working properly. But we already tested our 2-to-1 mux. And that was working fine. I guess let's go ahead and take a look, though. Let's go back to our 2-to-1 waveform file, mux 2 to 1 dot VCD. Maybe I was taking it for granted that this was working properly. It was. Oh, you know what? You know what happened? We didn't fix this like we were supposed to. We changed that to be messed up, and it was still messed up. So now let's run again. There we go. That's more like it. Mim says, why does it say A equals C? When did we say, when, I don't know, when, where does it say that? Oh, I see what you're saying. That's actually a good question. It's the next thing I was going to talk about. I know what you mean. No, so you're saying here, where it says A is equal to C, yeah? So this is because it's in hexadecimal, right? We set in our test bench, A was equal to 12. GTK wave by default will list everything out in hexadecimal. And 12 in base 10 is C in hexadecimal. If we want to, we can change this. We can say, I can right click on it. By the way, you can also double click and you can see all of the bits individually laid out and watch them change or whatever's going on there. But if I right click here and hit data format, I can now change it to decimal, and now it says that A is equal to 12. Same thing, I can come down here and change this to decimal, and now it's changing to 12. So that's why. So for the first 20 nanoseconds here, C is undefined, which means that Y is undefined, and as soon as C gets a value of 0, it takes the value of A, so Y goes to 12, and then 20 nanoseconds later we click C over to 1, and now it's going to take, Y is going to take the value of B, which is 6. Yeah, it was the number, the hexadecimal number C, not the, not a variable C. So, like I said, but you can right click on it and pick from a whole sort of list here of things that you could possibly look at, right? We could change it to binary and we can actually see 1100 instead of that. All right, any questions about that? Okay, we are out of time, but I still want to go ahead and show you a couple of other ways of implementing this. So I'm going to comment out. I'll go pretty fast, and we won't test bench them all. But the first one is we had to copy and paste all this and lay it in a whole bunch of times. Now that can be pretty time-consuming, especially if you have a lot of bits. Right? If you're making a 64-bit thing, then that's an awful lot of copy and pasting. So what we're going to use instead is what's called a generator. And to start that off, we need a what they call a gen_var, generator variable. We'll name it I. And then we need a generate block. So generate and end generate. And in here, we'll actually use a for loop. So for I equals, I'm going to start up at 3. So I still want to go 3 to 0. So I greater than or equals 0. And I equals I minus 1. Begin and end. And in here, I will say mux 2 to 1. Doesn't really matter what I call it now. A sub I, B of I, C, and Y of I. So this syntax basically lets us write in just a couple of lines this right here. Now, of course, this took more lines than this took, but of course, if we were working with more than 4 bits, this becomes much simpler, right? We can jack this up to 63, and now we can make a 64-bit 2-to-1 mux by just changing that. So that's what's called a generator. The last one that I want to show you, comment that out, is by sort of taking advantage of, so this still used the 2-to-1 mux, but we can make our multiplexer without it all together, right? So I can comment out my include statement and just have these things. But one thing I need to change is I need to change my output to also be a reg, or register. This is a sequential logic construct that we'll start talking about next week. But for now, we're just going to do that. And then I'm going to say always at star, begin and end. Inside these parentheses, you're going to say this block, this always block, will trigger anytime whatever is in here happens. And when you put star, this says do trigger anytime any of the inputs change at all. So pretty much anytime anything changes, execute this block. And then I can say if, let's do this, C equals 0, begin and end, then just say Y equals A. Else, begin and end, Y equals B. So this is, from your other programming classes, might be a syntax that is much more comfortable for you and doesn't require any of the rest of this stuff. But this is also a valid way to implement the same thing. In fact, no, let's just go ahead and leave it there. So, in case you don't believe me, let's run Verilog again. BVP, GTK wave, append, and there you go. There's the exact same behavior, but now we're using this kind of much more C-style syntax. All right. So with that, that is all I've got for you today. I will get the project posted hopefully this weekend. If not, I'll get it posted on Monday. And yeah, we'll get started in chapter 11. We're going to keep having class in this format, this sort of synchronous sort of remote style class, probably for the rest of the semester. Here, I'll do one better, man. I'll put him right there. Let's see. Give me just a second. Let's see. There you go. Boom, 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 boom. Upload, 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 upload. There you go. There's all the files. Oh, so he asked, how am I choosing the command so fast in the terminal? When you're doing a lot of repetitious commands, the terminal will store your history. So if you just hit up and down arrows, you can like cycle through the commands that you have in the past, right? So since a lot of times in Verilog we use the same 3 commands over and over again, so I'll have to, like, you know, hit up 3 iVerilog, VVP, GTK wave, and so on and so forth. So yeah, use the up and down arrows on your keyboard to toggle between command, to like go back through your command history and find commands that you've already done. That's also really helpful if you've been doing a lot of stuff and you sort of like, man, that was a command I used, you know, like 6 hours ago. You can like go way up and try to find what's going on. So, all right, if there's nothing else, that is it for today. Have a good weekend. Be safe. Don't do anything crazy. And I'll see you guys on Monday, where we're going to start talking about Chapter 11 and talking about sequential logic. Yes. Liam asks, is the include statement at the top of the test bench a tilde apostrophe? It sure is, yeah.